Okay, sound check. Some problems as usual. Just give me 1 second. We will start in a couple of seconds. Okay, so. All right. Are you ready for some cool stuff?
Yeah, sure.
Okay. So today we discussed 3 different things. Well, actually 2.5. Direct product is kind of just one definition. So the first thing is the notion of homomorphisms and isomorphisms, and I want to discuss how to produce different homomorphisms. And the second thing is finite Abelian groups, and I want to discuss several things related to them. So in the first case, the homomorphisms and isomorphisms. Well, it turns out that, well, homomorphisms are more important than the groups itself. That's why, for example, category theory is so popular now. Well, but in general, it's a very hard task to produce a homomorphism between 2 given groups. It's really hard to describe. Well, there are some general tools, but they are not available right now for us. We're not ready for them. So that's why I will just describe several specific situations where we can produce homomorphisms and isomorphisms by hands. So no general tools here.
If groups are finite, that's quite easy task.
What again?
If groups are finite, it's quite easy task, I suppose.
Yeah, well, I mean, you can check all possible maps. Yeah, but
if we in group we have only 3 elements, for example, it's really quite easy to check.
Yeah, if you have only 3 elements, that's not interesting. For example, how many maps from G to H? If you like maps, not homomorphisms, it's the amount of elements in H raised to the power.
N power of n square. Yes.
Yeah. So n to the n. It's not the amount of operations, but the amount of maps from G to H. That's the amount of maps. And now you want to take from them only those maps satisfying the definition of a homomorphism. Well, believe me, it's not the best thing to do. For example, if G is Sn and H is Sn, the group of permutations, then you have n factorial raised to the power n factorial. How many computers can handle this number, like when n is, well, 5? I believe you can.
There is such computers that can handle it, for example. There is supercomputers.
Well, if n is equal to 100, then just forget about this. You will never complete your computation.
But some computers that cost about $100 million, for example, maybe can't complete this.
No, if you take this, then no computer can handle that. Believe me, there is no way you can handle this number on any computer. That's not the best way of doing that. You can do that, that's a brute force, but it doesn't work. That's why computer science is here, because when people started doing things just using brute force, they have had to wait longer than the universe lives. So, okay, so let me start. let me recall, first of all, the notion of a homomorphism just in case. So if we have two groups, G and H, then a homomorphism is a map from G to H, and satisfying these conditions like G1 times G2 goes to the same thing as G1, 5G1 times 5G2. So this is a homomorphism. And if you additionally add the condition that phi is bijective, so you take all of this and additionally this one, then this is an isomorphism. So, and philosophically, isomorphic groups are the same. So if there is an isomorphism between G and H, they are called isomorphic. So now let's discuss this problem. So we take as the group G, the group Z plus. And as the group H, we take any group. I already discussed this during the lecture, so I want to recall what is going on here. Then I want to produce a homomorphism from Z to H. I want to describe all possible homomorphisms from the group Z with addition to an arbitrary group H with multiplication denoted by multiplication. Like using, so in H I use multiplicative notation, in Z I use additive notation because I use addition. And as I already told you, if you want to produce a homomorphism, you need to fix some element, absolutely any element. And then using this element, you produce a homomorphism which takes an arbitrary integer k to the kth power of the element H. And these are all possible homomorphisms from Z to H. So there are as many homomorphisms as many elements in the group H. So each element of the group H gives you a homomorphism from Z to H. So now I want to demonstrate this on several examples. So, well, it's not that interesting. So, but I mean, okay, but one remark before. So Z is a very good group. It's very easy to produce a homomorphism from Z to any other group. This is the rule. Before we proceed, are there any questions regarding this rule? Okay, so now let's consider homomorphisms from the group Z to the group Z6. Let's describe all possible homomorphisms from Z to Z6. So we know that there are 6 elements in Z6. Okay? So there are 6 homomorphisms from Z to Z6. Okay? So Z phi 0. Could you, so I will write all them down, and I would like to ask you to tell me what should I write on the right hand side for each map. So I want you to write down the right hand side, the image for each element. And phi 5 will be the next one. So what will be the image of K under the phi 0 map using this notation? Could you tell me what should be written here?
One.
Why?
Because K
Every number to the power.
one to the power there is 1.
But that's almost correct. There must be 0. because here we use additive notation.
Ah,
So h here is 0, but since the operation is additive, then h to k in our case means h plus h k times, which is k times h. Okay?
okay.
So it's k times 0. So that was the only trap here. So here we use multiplicative notation, and let me write it down for the additive notation. For the additive notation, you use this. So in the first case, we use multiplication, and in the second case, we use addition. Okay? So now, is it clear what should happen next? By the way, do you have any question? Is there anyone who doesn't understand what's going on here, or why we wrote that, or any other questions? Okay, so now what should be here?
K.
Yeah, just k. Well, formally we should say k modular 6, but it's the same thing as k. Yep. The next one.
2K.
Yep. And now I believe you see the pattern, so it's not interesting. Then it will be 3k, 4k, and 5k. And these are all possible homomorphisms. And also I should write modular 6 all the time. So these are all possible homomorphisms from Z to Z6. Do you have any questions regarding this?
No.
Okay, let me take these two homomorphisms. The first one is this, and the second one is this. I want to recall you the definition of the kernel and the image, and I want you to compute the kernel and the image. Well, we'll compute it together, the kernel and the image of these two homomorphisms. Okay? So what is the kernel of a homomorphism? It's the set of all elements. In our case, is the set of all elements in k in Z, such that phi of k is equal to 0, because we use additive notation on the right. So just want to compute all the elements going to the neutral element on the right. And the image is just the set of all elements of this form, where k goes through all integers. And it will be inside Z6. And this is inside Z. Okay? So, oh, by the way, what is the image and the kernel for the first homomorphism? Let's start with the simplest possible case. What is the image and the kernel here?
Well, the image is only 0.
Okay.
And the kernel
And
is K.
Kernel is all the elements in the...
Yeah, the kernel is Z. Yep, exactly. Okay, now let's try describe the kernel and the image here. So I'll write it here. The image of phi 2 and the kernel of phi 2. So the kernel must be subset inside integers, and the image might be subset inside Z6.
So maybe image is 2, 4, and that's all? And 0?
Yep, 2, 4, and 0.
And kernel is 3? No?
Just 3.
Oh,
Three and
no.
Well, 3 is not enough. The kernel
Six.
must
3 times Z.
times Z. Yeah, 3 times Z. Yeah, exactly. So this is the kernel, and this is the image. Yes. Okay. And so how do we compute this? So we see that in the image we get all the elements of the form 2 times k. So these are all possible even numbers, and we take them modular 6, so we get only these numbers. So this is the image. And now, how do we compute the kernel? We want 2 times k to be 0 modular 6. It means that 6 must divide 2 times k. If we cancel out 2, then it means that 3 must divide k. So, and this is why we have this answer. Are there any questions regarding this example? Should I write down the computation that I orally explained just yet?
I think no.
Okay, that's good. Then what happens in the next case? So let me write it here. The kernel for 5, 5, and the image for 5, 5.
Why we compute only for this one, but not for others?
Well, because we will get almost the same result for some of them.
Oh, okay.
So, I mean, it's a waste of time doing it for all of them. If you wish, we could, but I just don't want to spend so much time on doing that. So let me show the rule. So this is the rule. So what is the kernel? And I'll show you the trick here. Okay, let me help you. In Z6 here on the right, 5k is the same thing as minus k modular 6.
Only 5?
Okay.
5 and 0 probably, no?
What again?
Kernel is 6 and 0? Oh no, not 6, sorry.
5.
5, yeah, 5.
No, the kernel, well, actually, the kernel will be 6z.
No, it's image. Image is 5 and 0.
The image will be this. The image, it's surjective.
Wow.
And the claim is that this map is surjective. Let me explain. So our map from z to z6 takes k to 5k modular 6, okay? But this is the same as minus k modular 6. You see? Because 5 and minus 1 are the same modular 6. Is it clear?
Yes.
So, but now it's clear that this map is surjective, because if you want to get an element m here, modular 6, just take minus m, then it goes to this element, because this element goes to minus k modular 6. That's the trick. So the map is surjective. So now, so that's why the image is Z6, and why the kernel is 6Z is because, again, we want this to be 0 in order to compute the kernel. So this simply means that 6 divides minus k, but this is if and only if 6 divides k. So this means that the kernel consists of 6z. Do you have any questions regarding this computation? Should I explain anything? Okay. Well, I will. Do you know the Euclidean algorithm to find greatest common divisor?
Yes or no?
Okay, and there is like an extension of this algorithm. If you have two numbers, m and
Yes or
n,
no? This we had this one discussion.
yeah, we have these presentation of the identity element. Yep. So now, what this means here. So actually, I'm using here in this case when I use 5. Well, you see. Okay. So let's divide this into pieces. I don't want to make this a mess. So let's stop with doing that, and I will switch to a different case. So now we wanted to describe all possible homomorphisms from Z to Z6 and compute their kernels. So in order to compute the homomorphisms, we take the identity element to an arbitrary element, and then every integer number k goes to a corresponding multiple, since we have additive notation here, or to the corresponding power if we had some multiplicative notation. And also in these three cases, we computed the image and the kernel. So if you don't have any questions, I want to switch to another thing. So now I want to compute homomorphisms from finite cyclic group to another group. So we discussed the case when the left-hand side was the group Z. Now I want to discuss the case when the left-hand side is Zn with addition. So this is our G, and I want to find a homomorphism for G to an arbitrary group H. So H is just any group. So how do we do that? Well, actually, it works in a similar way. So we should fix an element H in H capital, but now we have a restriction. H to the n must be 1. Not every element of the group H can be taken. Only the elements with this condition. And now, every homomorphism is described like that. This is for multiplicative notation. And for the additive notation, it means that k goes to h times k, and in additive notation, our restriction looks like this. N times h is equal to 0. So this is what happens here. So again, if you are given a group of reminders modular integer number n, then all possible homomorphisms from this group to any other group are described like this. You take an element here of order dividing n, which means that h to the n must be equal to the neutral element, and then every element with this restriction gives you a homomorphism. Or in additive notation, you take an element h such that n times h is equal to 0, and every rule like this gives you a homomorphism. So these are all homomorphisms from this guy to this guy. So the difference with the Z is that in case of the group Z, you don't have any restrictions on this element. You can take any element. But here, since we deal with this group, we have these additional restrictions. So we have less homomorphisms than if we would have in case of just the group of integers. So okay, if it's clear, then let's try to compute all possible homomorphisms from Z4 to Z6. And just in case, I will write down all the elements of the 6. So I want you to compute the elements. So what do we do at the first step? We should find all the elements here with condition for h is 0. Could you list me the elements with this property?
3,
0.
0,
3.
3. Any other elements?
Well, a should be either divisible by 3 or equal to 0, so I guess no.
Yep, that's all the elements, 0 and 3. So we have only 2 elements with this restriction inside Z6. So this means that we have only 2 homomorphisms from Z4 to Z6. One is determined by the 0 element and the other determined by the element 3. So we have phi 0 and phi 3. So how do they work? K goes to K0 in the first case, which is 0. And in the second case, K goes to 3K. Well,
So basically, there is a homomorphism from any group to any group. Yeah?
well, there is always a homomorphism which takes all elements of the left group to the identity element of the right group. So yeah, you always have such a trivial homomorphism. And it may happen that there is no other homomorphism. So it may happen that this is the only homomorphism, but yeah, you always have at least this one. Now, let's compute the kernel and the image. So the kernel of phi 0 and the image of phi 0, and also the kernel of phi 3 and the image of phi 3. Could you tell me what happens here in case of phi 0? Not Z, but Z4. The kernel is the whole, now the left-hand side is Z4, not Z. So by the definition, all elements go to 0. So this means that the kernel consists of the whole group, and the image consists of the 0 only. That's it. Yep. So what happens here? Well, let me speed up the things. So the image will be the set of all integer divisible by 3 modulus 6. So this will be the set of 0 and 3. And the kernel will consist of 0 and 2. Because we want all elements k from Z4 such that 3k is divisible by 6, which means k must be divisible by 2. And there are only 2 numbers here divisible by 2. These are 0 and 2. That's how you compute this. Okay, so this is a typical problem to compute all possible homomorphisms from one cyclic group to another cyclic group.
Excuse me, and why do we have exactly such mapping from k to h to the power k?
What again?
Why do we have exactly that mapping?
Why do we have exactly that mapping? Okay,
yeah.
Let me show you. So if we have like Zn and h, suppose we are given a homomorphism phi, okay? Then if we take phi of k, this means we take phi of 1 plus 1 plus 1 k times, okay? And since phi is a homomorphism, it takes this sum to this guy, 5 phi of 1 times, where we get also k times, and this is inside the group H. And this is the operation of the group H, this one. But now this is phi of 1 to the power of k. So if we know the value of our homomorphism on the element 1 of this group, then the value on any other element k must be given by this formula, okay?
Okay, thanks.
So now I just denote this element by h. So I take 1 to the element h, then all elements k goes to the kth power of h. And if we use additive notation, here we have plus, and here will be k times this thing, okay?
Okay, thanks.
And the reason why we have this restriction is because in this group, if you add the element 1 n times, you must have n from one hand side. From the other side, n is equal to 0 in this group, so it must go to the identity element. So let me show you. So in the group Zn, you have this 0 is equal to n, and is equal to 1 plus 1 plus 1 n times. So if you apply your homomorphism, it means that phi of 0 must be phi of 1 times, etc., phi of 1 n times. And it must be phi of 1 to the n, and it must be 1. So that's why we have this restriction. And some direct computation shows that if we take an arbitrary element h with this restriction, it gives us, so the map by this rule, if we are given an element with this restriction, the map by this rule gives us a well-defined homomorphism. So, I mean, this map satisfies this property that the operation is preserved. That's how it works.
Okay, thanks.
Okay, and let me show you one other example. If I take, say, Z6 to Z6, I can define a homomorphism like that. So I can take element 1 to any element co-prime with 6. For example, I can take it to the element 5. So k can go to 5k modular 6. This will be a homomorphism. So which is 5, 5, 5.
And can we build a homomorphism from Z6 to Z4?
Yeah, there are homomorphisms from Z6 to Z4. Do you want me to list them all?
If we have enough time.
Oh, okay, let me do it, but I will do it quickly. So from Z6 to Z4, so we know all the elements of Z4 are 0, 1, 2, and 3. So I want to take all the elements with the restriction 6 times h equals 0. What are the elements with this property here? Well, this
0 and 2.
0, 2.
Yep, 0 and 2. These are the elements satisfying this property, because the result must be divisible by 4. It's already divisible by 2. So in order to be divisible by 4, we need h to be divisible by 2. So that's why we have only 2 homomorphisms, phi 0, which takes k to 0, and phi 2, which takes k to 2k modular 4. These are all possible homomorphisms from Z6 to Z4.
Okay.
So yeah, we do it exactly in the same way. So yeah, and let me go back to the example here. What I wanted to show that this guy, well, in this case, this map is the same as this map. and this defines an isomorphism from Z6 to Z6 because it's just maps each element to its inverse. So it's a bijection and it's a homomorphism. So this is an example of an isomorphism between Z6 and Z6, which is not an identity map. Okay, just in case. Okay, we have enough time, and we have like 40 minutes. Okay. So now, let me see. Okay. Okay, let's switch to finite abelian groups. So this is more or less what we can do in the most general case. So let me summarize what happened here. So I discussed how to produce homomorphisms from the group Z to any other groups, and how to produce homomorphisms from the group Zn to any other groups. So at least this, how it should be clear how to do this. So you always list all the elements on the right-hand side, find the elements with the required restriction, and then each such element gives you a homomorphism defined by this simple rule. This for the multiplicative case and this for the additive case. Okay, now what I want to discuss is, let's deal with the direct product. So suppose we are given two groups, G and H, and I define G times H to be the direct product of groups where the set is just the Cartesian product of the sets and the operation is just the compound-wise operation. So if I take G1 H1 times G2 H2, this is G1 G2 H1 H2. This is how the operation works here. So if I need to tell you, like if I need to explain it in more details, please ask. But that's more or less all I want to recall regarding the definition of the direct product. So this Cartesian product with this component-wise operation is called the direct product of these two groups. Now, the interesting question is how to compute an order of an element in the direct product. So for example, we're given an element here. And suppose we know that the order of the element G is n in the group G, and the order of the element H is m in the group H. Then what is the order? Oh, I'm sorry, that's not what should be written here, G times H. So the question is, what is the order of these elements in the group G times H? What do you think?
Is it like the product?
Yeah, I'm sorry?
Is it like the product?
Yes, it's n by m, I think.
No, that's wrong.
Maybe n plus m.
No, the previous attempt was better. So let me write down all the possible answers. So the first answer was m times n. The second one was m plus n. Are there any other options?
Maybe it's something like least common multiplier.
Okay, yep, that's the right answer. That's the least common multiplier of m and n. And I want to explain why this happens here. Okay. So, so what is the order by definition? Oops, wrong color. By the way, before we proceed, is it clear what we are doing now? I mean, if you have any questions regarding what's going on, please ask, because if you don't understand what we're doing, it's better to stop and explain than you will listen something that you don't understand. So are there any questions? Okay, so we have this pair, and we want to find such a number k that the result is the identity element, which is the pair consisting of the identity elements of the groups. So this is what we want. And we want k to be positive and least possible. Okay?
Yeah.
But by definition, the left-hand side is the same thing as g to the k, h to the k. And it must be this guy. But since the pair is equal to another pair if and only if each coordinate is equal to each coordinate, then this is the same as saying that we're looking for k with this property, such that k is positive and the least possible. Okay?
Yeah.
So, but now we know that since the order of g is n and g to the k is equal to 1, it means that n divides k. The order of element divides this power. And the same thing, since the order of h is m, then the second equality implies that m must divide k. But now, since both numbers divide this number k, it implies that the least common multiple must divide k. So the smallest possible positive k must be equal to the least common multiple in this situation. So that's the explanation why the order of this element is the least common multiple. Do you have any questions? For example, why this is true or why this is true? Do you have any questions regarding any implication in the proof? Okay, so it's clear. That's good. So that's this simple rule explains how to compute the order of elements in a product. So for example, if we're given like something like z2 times z3, we can compute the order of every element here. So for example, in z2 we have element 0, 1. In z3 we have elements 0, 1, and 2, and we know their orders. Here, what is the order here? It's 1, and the order is here 2. The order here is 1, and the others here are 3 and 3. Yep. So now, if I say give you an element like 1, 1, what is the order of this element?
6.
Yep, it's 6. So, and if I give you like elements like 0, 2, its order?
3.
Yep. And that's the general rule. So if you need to compute an order of an element here, this is how you do it. And why is it important to compute an order of an element? Well, for example, if you want to produce a homomorphism from a cyclic group to this group, then you want to compute all the elements like of some specific order or satisfying some condition like 6h is equal to 0, something like that. So that's why you want to solve this problem. These two problems are related. Okay, so now I want to switch to a different problem. So I want to discuss the Chinese remainder theorem. Let me recall. So we have two integer numbers, m and n. They are natural positive, and they are coprime. Then this group is isomorphic to this group. And the map from the left to right is given by the rule k goes to, let me write it like k, comma k, where I mean that here I take k modular m and here k modular n. But it's simpler to remember the rule if you write it like this. Just k goes to k, k. In particular, if you take, for example, z6, it must be z2 times z3, and the map works like this. So an interesting question is how to find the map in the other way. So we want to find the map here. And this is the question I want to address now. So, so the Chinese remainder theorem tells you that this map is an isomorphism, so it means that there is the inverse map. So let's try to find the inverse map explicitly. By the way, is there anyone who knows the answer, how to do that? Okay, so let me show you, let me explain the general idea. So the idea is this. So first, we want to find two special values. The element, say, how do we call them? Okay, I want to find a number x in Zm, which goes to element 1, 0. And I want to find the number y in Zmn, which goes to
I have an idea. Maybe we should like multiply a by n and plus b, like na plus b. Can we do so?
Could you repeat?
Like, for example, a multiplied by n plus b, or b multiplied by m plus a.
So these are two options that you. Yep.
Yeah.
Well, these two options are incorrect.
Okay.
It doesn't work. Well, we can check that it doesn't work. It's a bit more complicated, and you will see why. Okay, so well, you need to. Okay, your formula is almost correct. You have to add some multiple here, and you want to add some additional summand here. So you want to correct this formula a little bit, but you're almost correct. So let me erase this because I need the space. So let me show you how it should be done. So first of all, you want to find some special elements, x and y, which correspond to the elements of this form. So x belongs here, so it's just an integer from 0 to mn minus 1. So if we know these two elements, so we know we have an isomorphism, then the element of the form, oops, ax plus yb correspond to the elements ab. Is it clear?
Yes.
Is there anyone who doesn't understand why, if we have these property, then it implies that we have this? Is there anyone who needs an explanation? Okay, so but then we may invert this formula, because if this element goes to this one, then it simply means that well, the formula works in this direction, like because it's a one-to-one correspondence. So the element A, comma B goes to this sum. So now the only problem is to find explicitly these elements X and Y. Okay. And here we will use the Euclidean algorithm to compute the greatest common divisor. So since M and N are coprime, we know that we can present one in a form U times M plus V times N, where U and V are some integer numbers. So we can find them using the Euclidean algorithm. But then try doing this. I will move U times M to the left hand side. Then we will get 1 minus U times M is equal to V times N. Let me denote this number by X. So since this is equal to this, there is no difference between the definitions. I mean, this or this number, they are the same, so this will be our X. Then, by definition of the map, from here to here, let me recall it. So the number K goes to K modular M, K modular N. So the element X goes to X modular M, X modular N. But since X is equal to this thing, it equals 1 modular M. And since X is equal to this thing, it's equal 0 modular N. So that's how we found the element X with the required property. Is it clear? Should I repeat this or explain any details? Okay, if it's clear, then could you tell me the definition for the element Y?
Like UM.
Again?
UM.
Yep, it's U times M, or the same thing as 1 minus V times N. And you see, if I substitute here instead of X, Vn, so let me write this formula explicitly now. So the pair AB goes to A times X, which is V times N, plus B, and here I will use this notation, 1 minus Vn. And as you remember, the formula that was given before was missing this and this. So it was almost correct. So I have to correct this summoned by multiplying it by V, and here I have to correct this formula by subtracting this term. So those formulas were almost correct. Okay, so let's try to compute. Now I want to apply all these formulas in this particular case. Okay, let me repeat it here. So we have Z6 is isomorphic to Z2 times Z3. And I want you to compute where the element 1, 2 goes. So probably it's better to ask where 1, 0 goes and where 0, 1 goes. So this is our x, and this is our y, and our numbers are 3 and 2 and 3 in this order. This is our m, this is our n.
So y is 3, isn't it?
No, x is 3.
Oh, yeah, sure. Excellent.
So here we have 1 is equal to 1 minus 1 times 2 plus 1 times 3. So this is your u and v integers, okay? So if you want to apply this rule, so and this is your m and this is your n, and now you want something which is so for finding x, oops, yeah, you move this to the right hand side, and for finding y, you move this to the right hand side. So actually, this is your x, and this is your y. So x is 3 and y is minus 2. But minus what is minus 2 here? Since 6 is equal to 0, minus 2 is the same thing as just 4. Modular 6, there is no difference between minus 2 and 4. So these elements goes to 3, and this element goes to 4, or minus 2 if you prefer. If you are not afraid of writing the formulas for the elements here. So is it clear? I mean, do you have any questions, or is there anyone who has any troubles with this explanation? Okay.
And why do we take minus 1 as u?
Why do we take minus 1 as u?
Yeah.
Well,
Do you just guess it or like calculate?
How did I find that?
Yeah.
Well, there is an algorithm, which is an extended Euclidean algorithm, which explains how to do that.
So you just calculate and learn.
Yeah,
Okay.
I pre-calculated that. So, but when these two numbers are small, I just guessed them. So I just try to combine different options for u and v, and then when I see, okay, this option is okay, I just use them.
And how is the fact that a is equal to 1 and b is equal to 0 used here?
Again, which could you just repeat?
How is the fact that a is equal to 1 and 0 is equal to b? For example, we have that 1 0 maps to 3. How
Yep.
How 1 0 is used here? This pair.
How the 0 is used here?
1 0 pair.
It's not clear to me.
What's the sense of it?
the question,
So how does it affect the result? That it is 1 0 2 0.
Okay. If you choose if you change your u and v, will it change the result? That's your question.
Yep. No, I don't understand the correlation between 1 0 and the numbers you guess or calculate.
1 0.
How do they,
I don't understand the question.
They are related to each other.
How these elements are related to each other?
Yeah.
Well, okay, the elements of this group are all possible pairs of elements from here and here. I just take this specific element from this Cartesian product. I just want the right element to be the neutral element here and the left element to be the generator here, and that's all. I just want to consider this element. I just want.
Okay, and how do we get from it that x is equal to 3?
How do we get that? Okay, so that was explained here. So let me repeat it in this particular case. So you see this equality for the greatest common divisor. Now let me do the blue action here. So I write 1 minus 1 times 2 equals 1 times 3. Okay? I just want to denote this by x. And now, so that was my guess. So let's try to check this element. So now I see that from one hand side, since there is 2 here, then x is equal to 1 modular 2, which is exactly what we wanted here. We want x to be 1 modular 2, because map from right to left is like this. K must go to k modular 2 and k modular 3. So if we somehow we are trying to find k which give us 1 modular 2 and 0 modular 3. So because of this equality, this number x is equal to 1 modular 2. And because of this equality, like x is equal to 1 times 3, then x is equal to 0 modular 3. So we found exactly the element we needed. We found an element which goes to 1 here and 0 here. So since it's an isomorphism, it means that when I go in the opposite direction, this element must go to this element. Must go to this element. Sorry. Now, is it clear what I'm saying?
Now it's clear. Yeah, thank you.
But was that the answer to your question? Because I'm still not sure that
Yes,
I was.
yes. I didn't understand. Yeah, so now I understand it. Thank you.
Okay, that's good. Because I wasn't sure that I understand your question. So, okay, that's good. Okay. So, oh, now we have like 13 minutes. Okay, so let's switch to the final part. I want to deal with the classification theorem for finite abelian groups and discuss several problems. So now, if we are given a group like, say, Z6 times Z10 and Z one second. Oh, let me change this. I'm sorry, Z3. No, I'm sorry. I'm looking in the wrong place. Oh, okay, okay. Z10 times Z3 and Z5 times Z6. Okay, so I want to check if these two groups are isomorphic or not. So there are two possible ways to check it. We should present both groups in one of the two forms I discussed on the lecture. So let me recall the two forms. The form number 1 is this, where each order divides the next one. And the form number 2 is this, where pi are prime. They may they may repeat. It doesn't matter. So I want to represent our group in one of these two forms, each group, and if the form these well, for example, I want to represent in the first form, and if the first form for both groups are the same, forms are the same, then the groups are isomorphic. If they are not the same, then the groups are not isomorphic. And how do we do that? Well, we use the Chinese remainder theorem in order to switch the form of this group. So in the first of all, is this group in one of these forms or not? For example, is this group in the form 1?
Yes. No, 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 no.
Even if I change the order of the factors, it's not in the form 1 because 10 doesn't divide 3 and 3 doesn't divide 10. And the same for the second group. 5 doesn't divide 6 and 6 doesn't divide 5. So it's not in the first form. So let's see if it's in the second form.
Yes.
Are there any?
No, no.
No, because 10 is not power of a prime number. It's a product of two different primes. So it's not in the second form because 10 is not like 3 to the power of something. But this factor is in the required form. Is this in the second form?
Nope.
No, by the same argument, because 6 is not a power of a prime number. So neither of these groups in neither of these forms. So let's compute the second form. It's usually easier to go to that. So Z10 times Z3 is what? We apply the Chinese remainder theorem to the first factor, and it goes to Z5 times Z2, and then times Z3. And now this is the second form. Okay? So the same algorithm is applicable to Z5 times Z6. We say, okay, Z6 is Z2 times Z3, and this is also the second form. And we see that this form is exactly the same. So the forms are the same. So these groups are isomorphic. So this was the group G, this was the group H. So they are exactly the same groups, but they're written in a different form. And now we want to find an explicit isomorphism from G to H. How do we do that? We take an element AB from here and apply the isomorphism from the Chinese theorem. So it goes to some to the element A, B here. Okay. No, well, I mean here A modulo 5, A modulo 2, and B here. And then, so let me write it here. So it corresponds to the element A, B here. And then we won't go to here. We apply the inverse map from the Chinese remainder theorem here. So it goes to A, and here we round down this formula AX plus BY, where X and Y are the corresponding numbers. So this gives us the explicit formula for the isomorphism from this group to this group. So is it clear how to get this formula? I mean, so now the only thing we're missing is these numbers, X and Y. So we applied the map here for elements 2 and 3. So we computed X and Y here in this example. So X is 3 and Y is 4. So we can write this formula more explicitly. So it goes to A, comma, so A times 3 plus Y times 4. Or we can even write it A, 3A minus 2Y, something like, because 4 and minus 2. Hmm?
Isn't it B?
Oh, you're right, it's B. I'm sorry. And here it's also B. That was my bad. I'm a bit in a hurry because I want to discuss one additional problem. So in general, when you are when you need to produce an explicit formula, you just do all the steps using the Chinese remainder theorem. You may have more steps than just 2, like here, and you just apply the rules in each case, and then as the result you get your final formula. So the isomorphism from here to here is given by this formula: A, comma B goes to A, comma 3A minus 2B. That's the final rule, how you go from here to here. And if you want to write down the isomorphism in the opposite direction, you just take an arbitrary pair. Here, goes here, and goes here. So, and you need the required formula for these two arguments here. So it can be done in the similar way. Okay. So now I want to discuss one final problem. I want to discuss how to compute how many finite abelian groups of a given order. Okay. So for example, if I want to compute how many finite abelian groups of order 8, like, so how many, so suppose that G is finite abelian group and it has 8 elements. How many are there? So how do you get all of them? So in order to do that, let's see. We know that each finite abelian group has a unique presentation in this form. So the only thing you need to do is to find all possible presentations of this form for your finite abelian group, such that this group has exactly 8 elements. So, but how do you compute the amount of elements here? It's just the product of these numbers, the product of the orders of the groups. So if I want to count, if I want to list all the possible abelian groups of order 8, then you see I write it as a product of powers of primes. In this case, it's just 2 to the power of 3. And now I have these options. I have z 2 to the power of 3, just one just one factor, or I have 2 factors, z2 times z2 to the power of 2, or I may have 3 factors, z2, z2 times z2 times z2. And there are no other options. I mean, there are no other options for this presentation to get 8 elements. So these are all possible ways to define or to get a finite abelian group of order 8. Well, now, is it clear what I did? Do you have any questions regarding this computation? Okay, so now I want to do a similar thing, but in case the order of G is 36, which is 2 to the power of 2 and 3 to the power of 2. Now, we have these options. So we must have summons of the form z with index 2 to the power of 2, or 2 to the power of 1, or 3 to the power of 1, or 3 to the power of 2. So the possible building blocks for our finite abelian groups are these. And we want to get from those blocks as many ones to get 36 elements total. So, and we see that in order to get, so the options are these: z2 times z2, or z4, or z3 times z3, or z9. And any combination of these 2 options are possible. So there are 4 options: z2 times z2 times z3 times z3, or z2 times z2 times z9, or z4 times z3 times z3, or z4 times z9. So here we have 4 different possibilities for our group. I'm sorry for being in a hurry. We lost like 5 minutes at the beginning because of the mistake with dispatcher. So now I have to be in a rush. So is it clear what's going on here? I mean, who think that he understood the way of computing all the groups of order 36? Is there anyone who understood this?
Does so what is meant to compute? Just to show what the group is?
What the reason of this computation?
Yeah.
I want to list all
No, what does
possible
it mean to
groups.
compute? To list all the groups.
Yeah, I want to list all the groups of order 36. And here is the list. So let me write down the list. I will write it with the blue color. So Z2 times Z2 times Z3 times Z3. Then Z2 times Z2 times Z9. Then Z4 times Z3 times Z3. And Z4 times Z9. So these are all possible groups of order 36, finite abelian groups of order 36. There are no other groups, finite abelian groups of order 36. So this is the complete list. So what you do, so you factor this number into powers of prime numbers. For each prime number, you write down all possible options. Like here for 2, I write like this. So here I have 2 must be here 2 times. So in this presentation, 2 must be here 2 times, like 1 to here, 1 to here, or the same 2 in the same factor. And the same for the number 3. 3 must be here or here in 2 different factors, or it must be in the same factor here. And then you take all possible combinations for this case and for this case. And that's how it works. Is it better now? Is it clear
Yeah,
at least? So yeah, so in general case, when you want to compute all possible groups of a given order, so you just repeat this algorithm. You factor the order into a product of powers of prime numbers. For each prime number, you compute all possible groups of this order. So here we computed all possible groups of order 4, which is 2 to the power 2. And here we computed all possible groups of order 9, which is 3 to the power 2. And then we took all the pairs from this and these cases. So if we had like any other prime here, then we need to list all the options for the remaining prime, and then take all possible combinations between all the cases, like 2 combinations here, 2 possibilities here, 2 here, and for example, like 3 possibilities here. Then we have like 2 times 2 times 3 options, and so on. So that's how it works. Okay, guys, I'm sorry for being in rush at the end. We're running out of time. Actually, we have -3 minutes left. If you have any questions, please ask. If not, then thank you for being here. I hope it was at least interesting.
Is it okay to
the
ask
seminar.
some questions via email?
Again, yeah, if you have any questions, just send them by email. And by the way, I forgot to mention, I posted the information about meetings. Like well, I have the Zoom translation at Wednesday since like 4 p.m. till like, I don't know, till the midnight. So if you have any questions, you can join, and you may ask any questions there. So just feel free to join.
Sorry, can you send us the video of the seminar? Because I just misunderstood some things and I want to revise it myself.
Oh, you want to watch the video?
Yeah.
For this? Okay, well, as I know, so the manager must provide you with the links to all the videos for all the seminars. If they did, so did they send you all the links for the previous seminars?
No, we do not have any video recordings at all.
Oh, that's a shame. Okay, thanks for saying that, because okay, I will write to the manager just right now, and we will solve this problem, because all of those videos, they are on YouTube. And I will ask them to make them public.
Okay. Okay, thanks a lot. Thanks.
The
Thank you very much.
seminars online.
Thank you for watching. Bye.
Okay, also, excuse me.
Yep.
You told that we can join you on Wednesday. Where can I get the link for that?
On the wiki page for this course.
No, okay, that's great. Thank you for the seminar. Bye-bye.
Thank you. Bye, guys.